Hello and welcome to this video on Thevenin's theorem. We've previously looked at several introductory examples to Thevenin's theorem, so if you haven't previously watched those, I would suggest going back and checking those out first, because in this particular video we're going to apply Thevenin's theorem to a more difficult example. And the example in this particular case is what's known as a bridge circuit. So the circuit that you can see on the screen here is this distinctive sort of diamond arrangement of components, which we call a bridge circuit. And we come across bridge circuits in a variety of different circumstances. One that we've mentioned previously is the bridge rectifier, a diamond sort of arrangement of diodes, which is used to convert or rectify AC waveforms into a DC electrical signal. And so in this particular example we're going to look at another bridge circuit. This is an example more commonly known as a Wheatstone Bridge, which is this diamond arrangement of resistors. And Wheatstone bridges are often used for a variety of different purposes, but largely to determine the values of unknown components. What can be done is, let's say one of our resistors here is an unknown value. We've picked a component that we don't know the resistance of. Let's say it's this resistor R3 here. We can actually make adjustments to the other or one of the other components until the bridge is balanced, and we'll talk about what we mean by balanced in just a second. But what we can do is we can sort of tweak the value of R4, say, which might be a variable resistor, until the bridge is balanced, and when it's balanced we then know the resistance of R3. In this particular video we'll talk about the notion of a balanced bridge circuit a little bit, but we'll also apply Thevenin's theorem to this particular circuit. And as you recall from our previous videos, the idea behind Thevenin's theorem is a simplification. We're simplifying this whole circuit down to one voltage across the load. Here's our load resistance here placed across the bridge, and one resistance, the resistance of the whole circuit, which we call the Thevenin resistance. Just another note on the topic of a balanced bridge circuit, which we mentioned earlier. If a bridge circuit is balanced, we expect there to be an equal voltage at this point here and at this point here. And what that means is there's no potential difference or difference in voltage between these 2 points. If that's the case, there should be no current flowing in this load resistor. So often when we're investigating the values of unknown components, like I mentioned earlier, let's say R3 is our unknown resistor, but we know the values of R1, R2, and let's say R4 is a variable resistor, we can adjust R4 until we get no current or measure no voltage across this this point between A and B. If that's the case, then our bridge circuit is balanced, and it's a series of simple calculations to calculate then the value of our unknown resistor. We're not going to do that in this video, but we are going to see whether or not this bridge circuit is balanced or not, and that's going to also help us determine the Thevenin voltage in this particular example. Let's begin first of all by giving our components some values. R1 in the top left there, let's say that is a 2 ohm resistor, so I'll mark that on there. R2, a 14 ohm resistor. R3 is a 3 ohm resistor, and R4 is an 11 ohm resistor. Let's also give our voltage supply on the left hand side a value of 54 volts. In the center, the load resistor, we'll give a value of 32 ohms. As is the case in all of our examples that involve Thevenin's theorem, Thevenin's theorem is an open circuit problem, and so as a result we remove the load resistor in order to begin our calculations. So here on the right hand side now is the same circuit duplicated, but rather than the load resistor being connected, as was the case on the left-hand side, we now have an open circuit, this pair of terminals on the right-hand side. For those who remember our previous videos on Thevenin's theorem, the first step of Thevenin's theorem was to find the voltage across the terminals using the potential divider rule. So in this case our terminals are here, and likewise we can still use the potential divider rule in order to determine the potential difference across these terminals, remembering what we said about a balanced circuit earlier on. If our circuit is balanced, we would expect our result, our voltage across these two terminals, to be zero. Let's see if that's the case in this particular example. To begin with, it might help to redraw this example very quickly. Though the bridge circuit is usually drawn in a sort of diamond arrangement like we see on the left-hand side, it's really just a pair of potential dividers. And so we can actually redraw our circuit a little bit more linearly by representing it like this, which will hopefully be a little bit more familiar to us. There's nothing remarkable or unusual about the fact that they're in a diamond arrangement, but it often throws people off what's a very simple calculation. So we can say here that R1 and R4 create this kind of potential divider arrangement, and R2 and R3 create the same potential divider arrangement. And so really all this question is asking of us is to find the voltage at the midpoint between R1 and R4 and the voltage at the midpoint between R2 and R3. And our Thevenin voltage will just be the difference between whatever we find those two voltages to be. Let's begin by looking at the first potential divider here on the left-hand side. We have R1 and R4. Let's stick some values on there. We know that R1 is 2 ohms and R4 is 11 ohms. We can use the potential divider rule to find the voltage at this point at the midpoint here with reference to the ground plane. We're going to assume that this is our sort of 0 point at the bottom here. And so the voltage at this point here is actually going to be the voltage across this resistor. It's the voltage between that point and ground, or 0, which is going to be the voltage across R4. So if we set up our potential divider rule, for now we can ignore R2 and R3. They're a separate potential divider and a separate set of equations. We can set up our equation something like this. We can say that V4, we'll call it, V4 is equal to our supply voltage, Vs, multiplied by a fraction. We put whichever resistor we're measuring across on the top, so in that case it's R4 goes on the top because we're measuring across that resistor here. So R4 goes on the top, and both resistors in the potential divider are added together on the bottom, so that's R1 plus R4. Putting some values in there, that's the same as saying 54 for our voltage multiplied by 11 on the top, 11 plus 2, or 2 plus 11 on the bottom. That comes out with a result of 45.692 volts. Let's repeat this exercise now for the potential divider on the right hand side. We've got R2 and R3 here. Let's give those some values as well. We know that R2 is 14 ohms and R3 is 3 ohms. So in this case we can do the same thing again. We are interested in this result for the voltage at that particular terminal, the midpoint, and that's the same as the voltage across R3, which is this bottom resistor in the divider. And so we can set up a very similar formula. Let's get rid of this one here. and we'll instead replace it with our second potential divider. So we can say in this case that V3, we'll call it, the voltage across R3, is the supply voltage multiplied by a fraction. We've got, in this case, R3 on the top, R2 plus R3 on the bottom, which is the same as saying 54, our supply voltage, multiplied by 3 over 14 plus 3. That comes out with a result of 9.529 volts. So now we know the voltage at this point here, on the left hand side of this gap between the two terminals. The voltage at the left terminal there is 45.692, we said earlier, and this voltage on the right is 9.529. So the actual Thevenin voltage here is going to be the difference between the two. So we can say, I'll put this at the top here, that our Thevenin voltage VTH is going to be equal to the difference between 45.692 and 9.529. And that comes out with a result of 36.163 volts. So there's our Thevenin voltage across that gap between the two terminals. Now the first thing to point out is, because we have a voltage here, this circuit is clearly not balanced. There's a potential difference between these 2 points. If there's a potential difference, it means that there's current is going to flow between these 2 points as soon as we put any sort of load across those terminals there. So this is not a balanced circuit. Either way, we've gone halfway now with our example of Thevenin's theorem. We've determined the Thevenin voltage. The second half now is to determine the Thevenin resistance. And it also helps to attempt to redraw this circuit in order to determine the Thevenin's resistance, the resistance between the terminals. So, in our previous videos on Thevenin's theorem, we said that the idea of the Thevenin resistance is to find the resistance from one terminal to the other. And that is the resistance going through the circuit, the internal impedance, as it were, from terminal, let's call it terminal A, to terminal B. Now, this is a very confusing example when we consider how it's represented currently. It's quite confusing to see how we get from A to B and calculate the total impedance, because it seems as though there's multiple paths from A to B. Remember, first of all, that in Thevenin's theorem, when we're calculating the impedance from one terminal to the other, we short out any voltage supplies. So once we've done that, hopefully, we can redraw this circuit so that it looks a little bit clearer. Let's begin, as we say, by getting rid of our voltage supply there and replacing it with a short in this case. So I'll just represent that by this red connection there. So we've short-circuited our supply from the circuit, and the objective is to find the resistance from point A to point B. Now hopefully it'll be a bit easier to visualize once we've redrawn this circuit, but let's start at point A, this first terminal here. Traveling from point A, the first thing that happens is our path splits. We can either go through R1 or through R4. So R1 and R4 we can think of being as in parallel. Let's begin our drawing at point A, and we can represent that hopefully by two parallel resistors like so. So we've got our two resistors in parallel, and they are R1 and R4. Then, regardless of whether we've gone through R1 or R4, we get to these points C and D that are actually just joined together by a wire. What we can do is simplify that a little bit. Let's remove this wire that's going all the way around the sort of extreme edge of the diagram. That wire was just joining points C and D, and so we could put that wire just as easily down the middle of our circuit here, like so. So points C and D are joined together. So what we can do is we can represent this on our diagram by drawing our two resistors R1 and R4 joining together. So this point here, we could call it C or D, C/D. We've got our two points joined. From that sort of common join between C and D, we can then go through either R2 or R3. This takes us to point B. And so the fact that we can split, we can either go through R2 or we can go through R3, means that we have another parallel arrangement of resistors. So we can draw those as well. So here's our two resistors in parallel, and they are R2 and R3. They meet together at point B, which is our second terminal. So hopefully when we redraw this diagram on the left hand side as this diagram here on the right hand side, you can see that it's not actually all that confusing at all. It's just two sets of parallel resistors both added together in series. So we can now work out the resistance between points A and B very easily. We can say that first of all the Thevenin resistance is equal to R1 in parallel with R4. That's just my shorthand, the double slash for two resistors in parallel. If you're not sure about calculating resistors in parallel, we've got a video on that much earlier on if you want to go back to that. Plus R2 in parallel with R3. Calculating the result of those resistors there gives me a Thevenin resistance of 4.163 ohms. So that's our Thevenin resistance there. Now that we know the Thevenin voltage and the Thevenin resistance, we can draw our Thevenin equivalent circuit. On the left hand side here we have our original circuit diagram right from the start of this video, and what we can do on the right hand side is we can draw our Thevenin equivalent circuit. We have a supply voltage, I'll move that very slightly, we have a supply voltage of 36.163 volts, and we have our single Thevenin resistance, so we'll draw that in series like so. We've got our one resistor there, and this takes us to our open terminal circuit like so, and we calculated our Thevenin resistance to be 4.163 ohms, so I'll mark that on as well, 4.163 ohms. And finally, one component that we've neglected in this particular circuit is our load resistor. So the last thing we'll do is we'll calculate the current that's going to flow in this circuit with this load resistor present. And remember, the current, if this circuit was balanced, should be 0. So let's apply our load resistor just as we've done in the original diagram there. Across the terminals we've now got RL, our load resistor, which we said was 32 ohms. And so the current that's going to flow in this circuit, I, is equal to Ohm's law, V over R. But in this case, we have two resistances. We have our load resistor and we have our Thevenin resistor, both in series. So we can say that V, in this case, we're using our Thevenin voltage in this particular circuit. So 36.163 over RL, which was 32, plus the Thevenin voltage of 4.163. That comes out as exactly 1 amp. So we're going to have 1 amp of current flowing across these terminals from point A to point B here. So clearly this particular circuit is not balanced, and we've illustrated that using Thevenin's theorem. So I hope you found this video useful, not only as an introduction to bridge circuits, but how we can evaluate them using Thevenin's theorem, and by redrawing them sometimes in a manner which makes them a little bit clearer to understand.